of today, Pierre Emmanuel Jabin, professor of mathematics at University of Maryland. We are.
Sorry, so I moved. I should
Oh,
have
you
said
moved.
that. I moved this summer. I'm at Penn
Oh, you
State
moved this
now.
summer. Oh, thank you for letting me know. Where are you now?
Penn State.
In Penn State. Ah, okay.
No,
So
not very far away.
not very far away. Okay. So he's now at Penn State University. Awesome. So no further ado, I pass the floor to you. Thank you again for joining us today.
Thank you very much. And thank you so much for the kind invitation. So what I want to do today is I want to talk about a relatively recent result that we obtained with, let me go at the beginning, with Didier Bresch and my former student Zhenfu Wang, and which consists in the derivation of the mean field limit for the Keller-Zegel system. Now, the actual result is, of course, relatively technical. So what I will do is give a very broad overview and a broad introduction of what all this is about, why we're interested in the mean field limit and things like that. And then I'll give you some technical hints of what's going on, but of course relatively limited, so that I really want to keep the talk broadly accessible. So system of interacting particles nowadays show up in a lot of different settings. And I've just tried to gather a few of them here. I'm not going to go through the list in details, just to give you a sort of idea of the various things that particles can mean. And, you can start from the classical systems, and plasma is the first one that comes to mind. Because this was the setting where the mean field limit was first derived formally by Lazov in the 30s. But of course, still in physics, astrophysics is another very classical example. Newton's equations for point masses, probably the first system of interacting ODEs ever to be written. And it's still used nowadays because for the study of galaxy formations, for instance, at large scale, the universe is mostly flat. And then you study concentration of dark matter. Dark matter particles are supposed to be interacting essentially only through gravitation. So it's a very common model. Of course, you have other examples in physics as in fluids, and I will actually go back to that later. But as I was saying, nowadays this has really spread in various other fields, from the biosciences, aerosols, microorganisms, to economics, social sciences. You have opinion dynamics, consensus formation, swarming, flocking, all things like that. And just to give two extreme examples of such systems. So this is an actual recent simulation, formation of large scale in the universe. And this is the dynamics of galaxies. And the color indicate the density, with, as usual, red indicating a higher density, blue a lower one, and the small yellow lines indicate the velocity of the galaxies. And at the other end of the spectrum, both in terms of applications, so it's biology instead of physics, and it's very small scale instead of very large scales, you have neural networks. And so here what you see is the cytoskeleton of the neuron. But this allows to observe relatively well both the center of a neuron and then the axons that connect them. Now, before going into the mean field limit, this is a slide that if you've seen me give a talk on mean field limits, this is the one slide that is shared by sort of all my talks. Because it gives a scale of what we mean by a limit. So basically the mean field limit consists in saying what happens when the number of particles, let's call that n, becomes infinite. But that's a bit of a mathematical formulation because in practice, of course, you have a fixed number, which can be very, very large, but how large is it? And so how close are we to infinity in various problems? And of course, if you're thinking plasma, for example, then order of magnitude is the Avogadro number. So around 10 to the 24, right? So range is 10 to the 20 if it's very dilute, to 10 to the 25 if it's more dense as a plasma. And as an order of magnitude for a physical setting, it's not, it gives you the right figures. But again, as I said, this is not the only use. And if you're now thinking microorganism, you're much lower. So how large is a bacterial population? Okay. And for example, and here it's useful to think of it between 10 to the 6, 10 to the 12, right? If you have a bacterial infection in your body, for instance, my usual joke is that 10 to the 6, you cannot detect the infection by taking blood sample, for example. And 10 to the 12, you're likely dead or dying. So that's sort of a range. This is also roughly the range of number of particles that you can actually put in a computer in a numerical solver. Right? So if I want to calculate the solutions to a coupled system of ODEs, how many particles can I use? Well, if you do things poorly, probably a lot less like that. But if you know a little bit what you're doing, you're using some fast multiple methods, for example, then you can ramp things up quite a bit. The best simulation I have seen so far was using 10 to the 14. But that's weeks of calculations on a supercalculator. And in quite a few other settings, the numbers can even be lower, right? I mean, if it's collective dynamics or swarming, I mean, how many animals are we talking about? Maybe a few thousand, you know, probably not that much more. So when you look at that range, right, it's relatively clear that there is a bit of a danger in talking about the limit n tends to infinity. Because while we believe that relatively well, if there's 10 to the 25, right, it does raise the question, well, how true is it for 10 to the 10? How true is it for 10 to the 4, 10 to the 3rd? And so the big point here is to say that whenever you can, sometimes you cannot, but whenever you can, having quantitative convergence result is so much better. Because then for a fixed n, it will tell you precisely how close you are to the limit. And then it's your decision to say whether the error is acceptable or if it's not. So what kind of coupled OD or SD, as we will see in a few slides, systems I'm talking about here? So let's take n particles, identical or exchangeable, as a probabilist would say. Now, this is a very important assumption. It doesn't mean that the trajectory of each particle is going to be the same because they may start from different places, but it means that if I swap them, then the system remains the same. So they have the exact same properties. Okay. If I'm considering plasmas, then all the ions in the plasmas have the same mass and the same charges, for example. You can do multi-species, but I'm not going to go into that during this talk. So I will represent all I need to know about each particle by a given vector in finite dimension, and I'm going to call that xi. So the kind of things that we put into xi is the position of the particle, sometimes the velocity, sometimes you add some internal state, right? Could be rotational velocity, for example, some internal energy. There are lots of systems. And if the particles interact 2 by 2, then what you get is pretty much the equation that is written on that slide. So you can have self-interactions. That's this term capital F of xi. And then you have a sum of 2 by 2 interactions that is described by some kernel k. And of course, the whole modeling question is how we would choose F, K, the initial data, things like that. But one important thing during all my talk, that is the second thing I want to insist on this slide, is this 1/n that you see in front of the sum. And this is what is called the mean field scaling. Now, its effect is very simple because I have a sum of n terms, right? And I'm divided by n. So formally, what that makes, it makes my sum of order 1. And I usually describe that as the simplest interesting scaling in such a system. It is not the only interesting scaling, right? There's no particular reason that once you put the physical constant and everything in, and you rescale time, and maybe you rescale position, velocities, there's no particular reason why you should end up with a 1/n in front of that sum. You will end up with some constant. But if that constant is a lot less than 1/n, then you don't get something that is very interesting. Because as n becomes larger, then you expect the interaction to go to 0. And that's not a lot of fun. On the other hand, if the constant in front of that is much larger than 1/n, then you probably have something relatively difficult to deal with because now the sum a priori could be very, very large. And so what that means is there are probably some pretty drastic constraints going on in the system so that, you know, you have the right configuration of positions, position velocities, things like that, so that the interactions have cancellations. And this is a lot harder. And of course, you know, another example of multi-agent system, many particle system, that has a much harder scaling is the one that leads to Boltzmann and collisional models. So here I will focus on that one, which again is far simpler, but still gives an interesting limit. So let's go to the first classical example, right, which I had mentioned, which is the Newton dynamics of point masses. So I consider now n point masses. So point means that I neglect the size of each mass, right, in gravitational interaction. So what do I need to track? I need to track their position, qi, and their velocity, vi. And I just apply Newton's law. So time derivative of the position is the velocity, time derivative of the velocity is the acceleration, which here is the sum of the gravitational interaction between whole particles. And this is the model that was solved in the first picture that I showed you, for example. It's also a model for which we still have no idea of whether the mean field limit rigorously holds or not. So it's kind of still very, very hard. But in this talk, what I will typically consider are a coupled system of stochastic differential equations. And the logic here is that I add a noise to the dynamics, right? And now it reads like that. So I have this plus square root of 2 sigma dwi. I put square root of 2 sigma because I will move relatively fast to a PD formulation, and I'd rather have sigma than sigma square over 2 in my in my equations and in my formula. This is just a question of notation. And the WI are just Brownian motions or linear processes that are independent. And there are several cases where you want to add noise like this. It can be because there's some sort of actually random effects in your model. And that can be random collisions, for instance, in the gravitational settings. This could be to try to model some sort of random behavior of microorganism, the run and tumble of bacteria, for example. It's not a great model for that, but it's at least something that tries to do the job. It can also represent some uncertainty in the system. And so because you're not very sure of what's going on, you just add noise in general to represent this sort of all type of other behaviors that can happen. Now, there are many ways of adding noise. You can multiply it, it's multiplicative noise. You can use other type of noise than Brownian motion. Again, here it's a little bit the simplest case. Note as well that here I'm fixing the size of the diffusion. It's also possible, and you have quite a few applications when you want to rescale the diffusion with a number of particles. And for simplicity, I'm going to look at the noise that is non-degenerate. In some models, it is degenerate, and I mentioned random collisions on gravitational particles. Random collisions only change the velocity, right? So then you would only put the noise in the velocity. Before going to the mean field limit, the first question I want to discuss here a little bit briefly is which kind of initial distribution we want to put on the xi0. Now, in many cases, when you have a time evolution system, there's an easy way to not have to make any decision on the initial data, which is to say, well, if we are trying to solve for an experiment, then the initial data is whatever the experiment provides. And unfortunately or fortunately here, that's not going to work. Because there is simply no way that anyone is going to give you the positions of 10 to the 20 particles with any kind of reasonable precision. So this is out of the question. There's no way to measure it, even very roughly. There's no way to measure it precisely on top of that. So this is doomed to fail. So we do have to make a decision on the initial distribution. And what people typically do then is they suppose that the initial distributions are IID or very close to being IID. And this is called chaos. And this follows the notion of molecular chaos that was introduced by Boltzmann in the mid-19th century. The logic to this is not only that we're making our lives simpler by doing something like that. A way to justify that, for example, is to say that those initial distributions, if you're looking at an experiment, are themselves the result of a long time evolution of some other dynamics. The dynamics is whatever was used to prepare the experiment. And if you assume ergodicity in that first dynamics, for example, then yes, the long time Gibbs equilibrium will look somewhat like something that is IID or close to being IID. Now, the idea of the mean field approximation is on paper relatively simple. You have this discrete force field, which is a sum of 2x2 interaction, and we are going to replace that by its expectation. And then instead of the original coupled system of SDE, now I have a different coupled system, which is called the Makin-Lazov process, right? And which is the second equation written here. The difference, of course, as you see when I write it like that, is just that as I have this expectation that is taken before the, all the interactions. And it's a conditional expectation, right? It's a conditional expectation knowing the position of the particles whose trajectory I'm trying to calculate. Now, this is not a coupled system of SDE anymore, because if I want to solve that, I need to find the joint law of particle 1, particle 2, and so on, till particle n, knowing particle I. So again, this is a different type of system. Now, the first question is why something like that would be true. And the second question is why would it be useful? I'm replacing a discrete sum of many, many terms by its average. So of course, I'm thinking law of large numbers. And it would be exactly a law of large number if I knew that the xi are independent. Not necessarily IID, but at least independent. But you know, just 2 slides before, I chose them initially to be independent. Of course, the problem is, even if they are actually rigorously independent at the initial time, there is no way that they remain independent as time goes by. And that's because the dynamics itself will correlate the positions. There's nothing you can do about that. That's what it is. So this leads to a relatively subtle notion, which is usually called propagation of chaos. And propagation of chaos is the conjecture that if n is large enough, then they might not be strictly independent, but they are almost independent in some sense. This is very fuzzy as I formulate it like that, but for a good reason. There are various definitions of propagation of chaos, depending how you want to measure this independence. And I'll show you in the second part of the talk, I'll show you the notion that we are using to get the result. Second question is, why is it useful? Well, it's useful because it turns out that this Makin-Lazov process can be greatly reduced. And if we show propagation of chaos, so if we can justify this, right, then we get to that. But now, if I take the same initial data for the xi bar 0 as I took for the xi 0, then they are IID or close to being IID. And it turns out that this system, this Makin-Lazov system, propagates independence. So they remain IID. Therefore, instead of solving for n particles, now I just have to solve for 2. And I get the second equation below for x bar 1, and then I would get the symmetric equation for x bar 2. And well, because I'm doing PD, of course, I'm greatly tempted to first look at the law, right, of each x bar I. Sorry, there's a typo, there's x bar I at the bottom. And well, if I'm using Ito's formula, I get an advection transport equation for the law, which is the Makin-Lazov PD. And that is this equation on rho bar. Now I have an n minus 1 divided by n because here I'm neglecting the self interaction, so there's no k of k of xi minus xi just goes away, right? So maybe I should have rescaled by 1 over n minus 1, but I didn't want to make it too cumbersome at the beginning. Of course, as n tends to infinity, this goes to 1, and so you get a PDE that is completely independent of n. So what the mean field limit does is it replaces at the macroscopic scale, right? So if you're looking at the distribution of particles, okay, rho bar, at the macroscopic scale, it replaces a potentially very complex, very difficult to solve coupled system of 10 to the 20 SDE by one nonlinear PD. And that's the whole point. Now, let me go into some of the models that I'm interested to solve. And the first one corresponds to actually a paper that we've done with my student a few years ago, but that gave the first idea of the method. And it contains the dynamics of point vortices in the fluid. So here's another experiment. This is a soap film, which is used a lot for images of that, because a soap film is sort of naturally 2D. And then, of course, it's relatively easy to see the velocity of the fluid in the film by looking at it, because it's soap, which is exactly you know, the game that kids play with the soap bubble and the nice color and all that. And here, what you see are some relatively well-defined vortices, which I found is very, very nice. So mathematically, what this corresponds to is essentially the Biot-Savart law, right? Which tells you that if you're in an incompressible fluid and you look at one point vortex, then this creates a velocity in the fluid that is given by this expression. And here I'm using the perp symbol to represent the rotation by pi over 2 in the trigonometric sense. And the dynamics of point vortices now just consists in saying, I'm going to put several such vortices in the fluid. And each of the center of the vortex is going to move according to the total velocities created by all the others. So the dynamic of xi is given by the formula below, and you just sum, right, over the velocity field created by all the other vortices, plus noise. Now here I'm looking at a relatively simple example where each vortices has the same vorticity, and in particular the same sign of the vorticity. And there are various issues, in particular if you allow to change signs, so but I'm going to skip. But I do make my life simpler by doing that. Now, if you don't put noise, this is a reformulation of 2D Euler. And if you put noise, this is not a reformulation of 2D Navier-Stokes, but it is conjectured, it was conjectured to converge to it. And this is actually a very old conjecture because it dates from the mid-19th century again, by Helmholtz. And Helmholtz's idea was to use this system of point vortices as a first way to approach turbulence in fluids. And again, mathematically, the formula are relatively simple. If I take the mean field limit that I had written, so if I take the system before, and I just introduce the Poisson kernel in dimension 2, then this Makin-Lazov equation exactly corresponds to the 2D Navier-Stokes written on the vorticity, so on the curl of u being the velocity fluid. And you have a very well-known system below. Now, another example, which of course is the one that I'm then going to focus on, are models of chemotaxis. And chemotaxis is simply the dynamics according to chemical gradients. So this is, again, an actual experiment that shows the dynamics of cells when you put some chemoattractant. And something that you observe in this experiment is that the cells do tend to congregate. Right? So you see those clusters of cells. we can do a very elementary basic model for chemotaxis in the following manner. Let's just consider one chemicals and denote by C its concentration. And then the simplest way of doing this is to say that the dynamics of one bacteria, again, we are going to neglect its size. So I'm just looking at its center. The center will move in the direction of higher concentrations of C. So it will move according to the gradient of C at point xi. And then I'm adding noise, which is a very rough way of modeling run and tumble type of behaviors of microorganism. It's not a good way by any means, but it's simple. And if I do that, right, I also have to calculate the evolution of the concentration. And the interesting case is when you have a coupling, and that coupling, for instance, can proceed from the fact that bacteria, microorganisms, produce the chemical themselves. So if they produce the chemical themselves, I should have a diffusion equation on C with source terms centered at each xi. And if I'm making one further assumption, which is that the chemicals diffuses much faster than the microorganisms are moving, then I can look at the stationary diffusion equation. And again, if I'm using the grain function, which is 2D log, I get the formula on C that is written below. Now, there could be outside external sources and then other stuff, but that's pretty much the basic one. And this is, of course, completely a toy model, right? It's not a very serious chemotaxis model in that regard. It has one, well, it has two virtues. One, it actually probably correctly gives the scaling of the interactions between microorganisms. So in a more complicated model, we should still expect that when microorganisms are close, for instance, their interaction should scale in a manner that is relatively close to what we have here. And the second virtue is it's very simple to study the actual limit. And it's a super well-known equation, right? It's what we nowadays usually call the Patlak-Keller-Zegel system. So the modeling idea that I showed in the previous slide was actually already done by Patlak in '53, but he didn't write the system. That was done independently later by Keller and Zegel in '70. And again, here, if I'm just writing down the Makin-Lazov equation corresponding to that system, this is what I get. There's also a fun fact that is, this is actually also connected to astrophysics because it looks very much like the so-called Smolchowski-Poisson equation that had been derived by Chandrasekhar in the 40s. All right, two bit of differences here in the way I'm writing it in comparison to the way we usually write it in PDs. Rho bar for me is a probability density. So it has total mass 1. And second, the way I use lambda, you see here, I put the 2 pi, which comes from the green function, explicitly in front of it. Now, as I said, this is a nice system. And in particular, we can pretty much determine its behavior. And it's interesting because obviously there is a possible self-reinforced loop in the dynamics. Because if you start having a little bit too many microorganisms at a point, right, then they are going to produce more chemicals at that point. And this in turn will attract more organisms, which will produce even more chemicals and so on and so forth. So there's a very natural question, which is, does this system blow up? And because it has a very simple structure, we can give a very precise answer. And here I'm quoting Bilbo-Pertam. There have been a lot of works on this. I just don't want to go over all the literature for this. So this is sort of a nice summary that has the clear-cut distinction. So it turns out that you have global existence or you have blow-up independently of the initial data. You just have to look whether the diffusion is dominant or the advection is dominant. So you have to compare lambda with sigma. And here, with the rescaling that I have done, the comparison is between lambda and 4 sigma, which actually corresponds to the critical mass that is 8 pi. If you do another rescaling where now rho bar doesn't necessarily have total mass 1, but you've rescaled the strength of the interaction and the diffusion. So that's the same critical regime. And if the diffusion dominates, so if lambda is less or equal than 4 sigma, you have global existence. And if the advection dominates, so lambda is strictly larger than 4 sigma, then you always have blow up in finite time. Now, I should add that if I look at the same system in multi-D, still with a log of interaction, so that's not Poisson anymore, right? Starting 3D and higher. So it's not this equation, it's this system and the mean field limit of this system. Then I keep the same behavior, and now the critical parameter is 2D sigma instead of 4 sigma. At the level of the multi-agent system, this raises so many questions. Starting with, do we even have existence? So does this coupled system of SDE even make sense? And that's hard because now you have singular attractive interactions between microorganisms. So if they start getting close, right, you might have problems. And the other issue is if you're thinking diffusion helps, well, at the level of a multi-agent, it probably does not, or not so much. Because the bad consequences of the Brownian motion is that it brings you near 0 with probability 1. So it's pretty much guaranteed that you will have some pairs of particles in this evolution that are going to end up being very, very close. And what happens then is delicate. So this was a big open conjecture doing the mean field limit for such a system. And now we'll finish this broad introduction by just quoting some of the main results. Now there is very extensive literature, so I hope you will forgive me if I didn't quote your favorite paper here. Just trying to keep it reasonably short. I want to emphasize 2 things. First of all, the deterministic case is now much better known than the stochastic case. In the deterministic case, for example, point vortices, the mean field limit was already done in the early 90s. So the mean field limit to 2D incompressible Euler. And you have result by Goodman, Hu, Lovengrub, and then result by Chauchet with more general initial data. If I am looking at strong repulsive interactions, then there is a very nice result by Serfati and Durings and Serfati for Riesz kernels. There's no result for singular attractive potentials of the type of Keller-Zegel, because without diffusion, that is most certainly ill-posed. The case that is not as well understood is the case of second-order system, even though there have been some great recent results by Pico in particular. And again, I want to emphasize that collisional models are a lot harder than all of this. The stochastic case, what we know is so much more limited. For 2D Navier-Stokes, for instance, there was a result by Ozada in the mid-80s, but this was only qualitative convergence plus a smallness assumption. The smallness assumption was only removed very recently by Fournier and Michler. And the first quantitative convergence was the paper with my student Zenfu 2 years ago. And specifically for the Keller-Zegel system, well, you see a lot of attempts, but very, very few results. The closest one is probably a recent paper by Fournier and Jourdain. And they show two things. They show well-posedness, and they show some sort of mean field limit. It's in the strongly diffusion dominant regime. There's another typo here. It should be lambda strictly less than sigma. So it's not 4 sigma, it's sigma. So this is not the critical mass. This is a regime where the diffusion is even larger or the interaction is even smaller, and diffusion is super dominant. But even this regime does not give you propagation of chaos, because the notion of limit that they get is so weak that we don't have any idea of whether there's uniqueness of solution at the limit. All right, so this is the end of this introduction. Now what I want to do is I want to go to the tablet because I don't want to lose you in the technical stuff. And I want to write down what we are doing. So let me first write down again the system. Right, so this is the object we have. And typically here, K is a gradient flow. And V is an attractive potential, right? So log X, if X is small, well, turn out that log X is negative, not positive. That's going to play a very significant role in the proof. I'm not going to show you that, but that plays a very significant role in the proof. So the first step for this is we have no idea what is going on at that level. And so the first thing is we're changing the point of view. And so what we're doing is we're looking at the joint law, rho n of x1, xn at time t. Now, something that I really have to emphasize right away because that's critical. This is not the whole information in the system. As a matter of fact, this misses every sort of time correlation in the trajectory. So this is losing information on the trajectory. which in some sense is the whole point of the method, because now we are looking at a statistical distribution and not at trajectories. And well, if I'm just using at least formally Ito's formula, right, it solves the Liouville or forward Kolmogorov equation that I'm going to write down in an abstract manner in the following way, right? So it's a linear equation in large dimension with an operator Ln, and Ln of rho n is just this sum over I of divergence of xi, 1 over n, the sum over j different from I, k of xi minus xj of n, minus, of course, the Laplacian in dimension, well, dn, right? So this is a simple but crazy equation. Now, I should add that for this equation, we can actually get existence of appropriate solutions, whereas we have no idea, again, how to do that on the original system. But I will come to that in 1 minute. Now, the problem with this equation is, of course, that there is no way to actually use it at the limit, right? You're not going to solve an equation in dimension n, and there's not much that you can do. So the question that is raised here is how to compare. Now, the first way that we had used with Zenfu to deny Navier-Stokes is to use the entropy of the system. And the Gibbs entropy here just reads something like that. And so that gives you a way to use a relative entropy. So let me define rho bar, the solution to the mean field limit, which is just this. And out of that, I can tensorize, and I can get, therefore, the joint law of the Makin-Lazov process. And then I can define my relative entropy between rho n and this rho bar n, so something like this. And now this is a very nice object that has nice property that allows to compare easily. And in particular, there's a fun convex property, which is that if I define a marginal rho n k, which is the integral of rho n dx plus 1 dxn, right? So those are sometimes called the observable in physics because those are the quantities you can actually measure, right? So rho n1 is the one particle distribution, rho n2 is the two particle distribution. That's going to give you correlations in positions, things like that. Then the relative entropy between rho nk and rho bar tensorized k times is actually controlled by Hn. So this is very, very nice because Hn is something that you will look at the level of the Liouville equation. And if you can get a good convergence rate for Hn, so if you can show that Hn goes to 0, then you will have convergence of all the marginals, and you're done. The problem is that for gradient flows, the time evolution of Hn is absolutely horrible. And that's because it creates a Laplacian of V. And if you try to go that way, then you're going to fail. So what was working for incompressible Navier-Stokes, where the flow is incompressible, right? So K is the orthogonal gradient of V. That means divergence K is 0. What was working there absolutely cannot work for gradient flows. And instead, what we try to do is we try to use the free energy. So the free energy is entropy plus energy, right? No big surprise here. And the energy turns out to be so what we are going to use here is, of course, the modulated energy. And this is exactly the object that Serfati is using for the Reese gases. So this En is going to end up being the right linear combination of our previous relative entropy with Serfati's modulated energy. And so let me write down what it is. This is the integral of rho n. And this is a modulated energy. So this is, if I'm in the torus, this is something like this. Where mu n is the empirical measure. Right, so if you choose all the xi according to rho n, then I can build mu n, which is a random measure now on the torus, and then I use it in the modulated energy. So R Kn, let me repeat that again, is the expectation of Serfati's modulated energy. And there's another way of understanding why this is so useful, which is to look at the Gibbs equilibrium. And if I define the Gibbs equilibrium like this, and I define the equivalent of the mean field limit of the Gibbs equilibrium, which is not an equilibrium for the limit, right? Because when I'm going to replace this discrete sum by a convolution, well, of course, I have to use the law at the limit, which is time dependent. And when I'm taking this limit, I have to be careful. There's an additional constant that shows up, which I'm going to write here. Then it turns out that Hn is a weighted relative entropy using the equilibrium. So the use of the right physics here is really important. It's the starting point. Writing down the time evolution of Hn is the first thing you have to do. I'm not going to show you what it looks like. It's reasonably simple if you trust you have the right physics, right? So you really have to use the structure of the equation well, otherwise you will get lost in the calculations. And I should mention we were not the only ones to try that. And the reason we succeeded is we actually used the right form of the calculations here. And that gives you a very nice theorem that I am going to write down just now. So we have certain assumptions. I need the limit to be smooth. I'm going to be vague here, and I need it to be strictly positive. So it cannot vanish. It turns out that on V, the main assumption is just an inequality. And this is very nice because this allows a much wider shape of V, so we are not stuck to the exact precise formula of Keller-Zegel. There are other assumptions of V, which is V, okay, if X is different from 0, that I don't want to write down here. And then I have an explicit Gromval estimate. That gives me polynomial decay in N. Now, so this gives you essentially everything you want to know. I'm essentially going to stop here. I do want to make one final remark on this. Note that I'm using the absolute value of Kn. I'm not using An directly. Kn does not have a sign. We are in the attractive case. So you actually expect Kn to be more negative than positive. This is the whole difficulty, the whole technical difficulty in the proof. For this, we had to develop new large deviation estimates. And this is really where things are painful. But it works, and it gives you what I think is a very nice result. So this is the first derivation of the first rigorous derivation of a Keller-Zegel system. It works up to the critical mass. And it works for a relatively broad set of kernels. So I think this is, this is a promising idea that should one should try to push further in various other cases. And there still remains plenty of questions, which is what happens if you don't exactly have a gradient flow? What happens if you start above the critical mass, but for times that are before blowup? And what happens for vanishing viscosity? There are all a whole set of other questions after that. But I will stop here, and I thank you all.
Okay, thank you so much for this beautiful talk. Is there any question? So you can either speak up or write on the chat.
Let me open the chat.
Okay. So if no one has any question, I do have one, which is more like a curiosity. I noticed that for those type of problems, they always use the Laplacian as diffusion, which gives the Brownian motion. What happens if you have coefficients within the diffusion? Is there physical interest in these kind of problems?
Yeah,
How does the math?
of course there is. The reason everyone using the Laplacian is that we already don't understand very well what's going on. Right? So, but sometimes it doesn't cost much to use something else.
I see.
In the previous result with my students on 2D Navier-Stokes, you can put a diffusion coefficient.
I see.
You can even put, as long as it's smooth, you can even put a non-homogeneous diffusion coefficient. You can probably put something else than Brownian motion, and it's still going to work.
Okay.
Here, it's a lot more complicated because we really need the Gibbs equilibrium. And the Gibbs equilibrium comes from using the Laplacian. So what would happen if now I had a sigma that was, a matrix, right? And here, well, I would want to have sigma -1, so you can still write it down, but I've really not checked what would happen with the calculations if you go there. It might be that as long as the matrix is not singular, then everything is okay, but I'm not going to. Again, I haven't checked. Okay.
Yeah. Okay. No, thank you.
I have a small question, maybe a related one, because you mentioned like people use mostly Brownian motion, and you get in the end a linear Laplacian. So do you expect that if you put something like Levy's light, then you get the fractional diffusion in the end?
For Keller-Zegel, I have no idea whatsoever, because the proof uses strongly the diffusion to control the Kn term, to control the modulated energy. For our previous paper, when we didn't have the modulated energy, yeah, I think this should work.
Maybe another stupid question. Is there some kind of relation of this kind of mean field limit with, I don't know what it's called, maybe scaling also from Boltzmann systems or Boltzmann equation to also diffusion processes and things like that?
Well, there are connections because the concerns are somehow the same. You need to have an adequate representation of your many particle system, and you need to have a way to compare with the mean field limit, which is not the mean field limit in Boltzmann case, with the limit, right? So when you look at it at a broader level, there are obvious connections. When you start looking down into the techniques, then they can be very, very different. And in particular, here what I get is I get a strong propagation of chaos. Because what I get is that if the initial entropy, initial relative entropy converges, then it keeps on converging. And that cannot be true for Boltzmann, because you start from an irreversible system. So entropy is propagated. And you converge to a dissipative system where entropy decreases in time. This is math entropy here, right? So they cannot fit. You cannot have convergence at the level of the relative entropy for Boltzmann, for example. So this method would completely break down by necessity.
But the reason for my question is because recently I think there are several works that devoted to showing in some diffusive limit, and you get the fractional diffusion from Boltzmann.
Yeah.
So it's also related to my question before. But thank you.
Yeah, and again, I mean, if you're looking at a broader level, then yes, you're going to be interested in very similar quantities. But the big difference in Boltzmann, which is going from reversible to irreversible, is going to break a lot of the structure that I'm using here.
Thank you.
You're welcome.
Okay. Any further question? So if not, let's thank our wonderful speaker again. Thank you so much for joining us to deliver this beautiful talk. And I pass over to Jan, if you want to say a few words.
Yeah, thanks a lot also from my side for our speaker today, Pierre Emmanuel. Thank you very much for being here, and also thanks everybody else for joining. Thanks Eduardo for being the host this morning. Yes, and please, as I just posted in the chat, feel free to join us again next week for a talk by Jose Carrillo. Same time, same place, and enjoy your week, everybody.